Alright, so this video is going to be part 13 of our sequencing series review. Okay, this video will be talking about Taylor and Maclaurin series, just constructing them from scratch to represent a function. Okay, this is the second video out of 2. I just wanted to get another example in there because these problems do tend to take a while. Okay, especially when you're explaining everything going through it. So we want to find a Maclaurin series for sine of x. Okay, so the first thing we need to do is take derivatives of our f of x and find patterns. Okay, so if we take our, actually I'll write f of x again down here because I don't want to erase this f of x up here. So f of x equals sine of x, f prime of x, well that's of course going to equal cosine x, and you can kind of just go through these derivatives here. Okay, you should be pretty comfortable with these by now. And after doing a couple of derivatives, you kind of see that this is just cyclic, but you're not going to know what your nth derivative of f is. Okay, you're not going to know what that is because, I mean, how could you, I guess? So, step 1 has kind of been a bust at this point. Now, what if we try to do step 2? Maybe we'll have more luck with that. Okay, well, if we plug in x equals a, remember our a is going to be 0 here. Because this is a Maclaurin series, so if you plug that in, f of 0, well, that's going to equal sine of 0, that's 0. What about f prime of 0? Okay, well, that's just going to equal 1. Cosine of 0 is 1. F double prime will be 0. F triple prime will be negative 1, okay, because you have a negative cosine of 0. Your fourth derivative will be equal to 0, and let's just do another one. It'll make things a little clearer later on. Your fifth derivative is going to equal cosine x, which brings you back to your fifth derivative of 0 equaling 1. Now, that being said, what will be your nth derivative at 0? Well, you're not going to know, are you? Right? And just like the nth derivative of f, when we're talking about just x in general, you don't know what that is, but you especially don't know what it is when you just plug in a number. Okay, so again, we won't know. Okay, so if this ever happens to you, which I'm pretty sure, I mean, I've definitely seen it happen with trig functions. I don't think I see it happen with anything else, but you just really want to start writing out terms of your series. Okay, so let's do that quick. Now, before we get into writing out the terms of the series, I put what we just had in step 2. Okay, I put that down here because that's going to be useful for what we're about to do here. Now, we have the Maclaurin series is telling us we're going to have the sum from n equals 0 to infinity of the nth derivative of f at 0 over n factorial times x to the n. Now, if we start out writing terms of this, okay, we have the 0 derivative of f, which means we don't take a derivative. That's f of 0 over 0 factorial, which is 1. That doesn't make this undefined. And this will be times x to the 0 power. Next, we have f prime of 0 over 1 factorial times x to the first power plus your second derivative over 2 factorial times x to the second power plus your third derivative over 3 factorial times x to the third power, and we'll just go up to 5 here. Okay, your fourth derivative over 4 factorial times x to the fourth plus your fifth derivative at 0 over 5 factorial times x to the fifth, and that's going to go on and on and on. Okay, and that's just writing out terms of the Maclaurin series. You can take your own time to do that if that didn't make complete sense to you, really. Just plugging in n equals 0, n equals 1, n equals 2, and so on. So, we know what these are. This f of 0, f prime of 0, f double prime. That's what we found in step 2. Okay? So, what we can do is actually put that in here. And what you'll see, actually, let's just say that this is equal to, well, f of 0, that's just going to make this whole thing 0. The whole first term is going to be 0 because f of 0 is 0. F prime of 0, however, is 1. So we're going to have plus 1 over 1 factorial times x to the first. Next, we have f double prime of 0, which we know to be 0. We'll just have plus 0 here. Okay. Next, we have the third derivative, which we know to be negative 1. So we'll have a plus negative 1 over 3 factorial times x to the third power. Okay. Our fourth derivative is 0, so that makes the whole term 0. And our fifth derivative, well, that is just going to be 1, so we'll have a 1 over 5 factorial times x to the fifth, and then that will go on and on and on. Okay, so what we're going to do now is we're going to reconstruct our own series, okay? Now, this series has just a bunch of zeros, okay? And those are useless. So what we're going to do is just get rid of those. So we're going to take this piece, and this piece, and this piece, okay? And all of the odd terms, actually these would be, well, this is n equals 1. So I guess you could say all the odd terms, okay? And we're going to put them together in their own series, okay? So we'll just have a 1 over 1 factorial times x to the first plus a negative 1 over 3 factorial times x to the third power plus a 1 over 5 factorial times x to the fifth power, and so on. Okay? Now this, we're going to say this equals to a series. We're going to not use n this time because we used n up here. So we're going to have this equal to k. We're going to say k equals 0 to infinity. Okay? And this is going to be relatively easy to set up, okay? We have, well, this is a alternating negative on the top, okay? It's in this k equals 1 term, okay? K equals 1 has the negative, so the negative is going to appear in the odd terms, okay? The terms with the odd k. So we're going to have a negative 1 to the k. Okay, that'll be our first step. Next, we have a x to the first power, x to the third power, x to the fifth power. Okay, so, well, how do we represent that? We can have an x here, but to what power? Well, what we could say is 2k plus 1. Okay, 2k plus 1 means that, well, we'll have a 2 times 0 plus 1, that's 1, okay? That gives us the first power. 2k plus 1, well, if we have a 2 times k, that's 2, plus 1 is going to be 3. 2k would be 4 here, plus 1 is 5. So that works out. And you see the factorials are doing the same exact thing, 1, 3, 5. So we'll have a over 2k plus 1 factorial. Okay? And right there, you now have your series. Okay, so that's basically it. And now we're going to find the radius and interval of convergence, and that'll be it. Now, since we're not dealing with two series up on the board here, I put these back to n being your variable. So let's go for our radius and interval of convergence here. So we're going to start off. Of course, we have a factorial here. It's pretty obvious what we're going to be doing here. We'll be doing the ratio test. Take the limit as n approaches infinity of a sub n plus 1 over a sub n. We don't need to worry about that negative 1 because that's just going to get rid of the absolute value. Will be getting rid of that. So we have an x to the, we'll have a 2 to the 2 times n plus 1 plus 1. Okay, and well, that's just going to be a 2n plus 2, right? And that'll be plus 1. So we have a 2n plus 3. Okay. So this can be rewritten as 2n plus 3. Now this will be over a 2n plus 3 factorial. Okay, it's going to be the same exact thing for the factorial because we still have that 2n plus 1. Now this is going to be all over x to the 2n plus 1 over 2n plus 1 factorial. Rewriting this limit to make it look a little bit nicer, we get the limit as n approaches infinity, the absolute value of x to the 2n plus 3 over x to the 2n plus 1, and that will be multiplied by a 2n plus 1 factorial over a 2n plus 3 factorial. Okay. So, we can simplify this down. We have the limit as n approaches infinity of, well, we have an x to the 2n plus 3 over x to the 2n plus 1. The 2n's go away, and you have a 3 minus 1, that's 2. So you have an x squared here. Okay. Now, on the for this one, we have a 2n plus 3 factorial in the bottom. Now that's the same thing as saying 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. The 2n plus 1 factorials will cancel, and you're left with 2n plus 3 times 2n plus 2. And that will be on the bottom. Okay? Now, as n approaches infinity, this denominator becomes infinitely large, and it doesn't matter what x you put in, it's going to equal 0. 0 is less than 1. Okay? And that means that your interval of convergence, okay, your interval is going to be from negative infinity to infinity. Okay? If it's asking for the radius of convergence, well, obviously you know that's going to be infinity. The radius of that interval is infinitely large as well. So, there you go. So you have your radius and interval of convergence, and you have your Maclaurin series representing sine of x. Okay? So, that is going to be it for this video. I just wanted to really show you another way of having to do a Taylor or Maclaurin series from scratch. Okay, you might not have something where you can figure out the nth derivative of f right away, so you know you'll need to write out some terms of your series and see if you can construct the series that way. Okay, but anyways, that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series and the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.